Welcome to my Cisco Scaling Network. This is the third installment in the CCNA material. Here we're doing a lecture review on Chapter 5. This is going to be the Adjust and Troubleshoot for Single Area OSPF. It's going to be an overview of OSPF from the Routing and Switching Essentials class, but again, it's going to focus mainly on Single Area OSPF. Chapter 6, our next chapter, will get into multi-area OSPF. So we're going to talk about, again, advanced single area OSPF implementations, and we're going to talk about troubleshooting it. So, again, after this chapter, you should be able to understand the designated router, backup designated router, how to modify the bandwidth, how to modify priorities, how the DR/BDR election process handles, and some, again, basic troubleshooting for OSPF version 2 and version 3. So again, first area of our main concept is our advanced single area OSPF configuration. So first question I have is, what's the difference between routing and switching? Switching is more about path forwarding. It doesn't do path selection, it just forwards data on the LAN. Where routing is scalable, and routing does path selection based off of layer 3. So again, fundamentals, we have to talk about static routing. Static routing is great in small scenarios where we only have 2 or 3 entries in a routing table, so that we can actually have the router that forward information based off of the static routes that are set. But as your network grows, that's going to be more difficult. Hence we have dynamic routing protocols. And it will be where they exchange routing information. And that way this makes it a little bit more scalable. So as we increase our layer 3 domains, this grows with us. So how do we configure how do we configure single area OSPF? Again, this is going to be different from multi-area, but right now we're just talking single area. You can manipulate bandwidth, but you don't have to. What we're going to do is we're going to assume we have one area, one sphere of control, and with that we'll have a process ID which is going to be the same on all OSPF instances in our network. So here we have OSPF, router OSPF instance 10 or process ID 10. That's to say we're all going to be using the same process ID of 10. And so once we all agree with that, we're each individually going to have dedicated router IDs to kind of distinguish each router in our process. So here we're using router IDs as router ID 1111 or router ID 2222, or if we're using router 3, router ID 3333. And we're going to have the appropriate network statements for each of these routers. So let's talk about spheres of control. So when we talk about our router 1 knows about these networks, hence those statements. Router 2 knows about those networks, hence those statements. Router 3 knows about those statements. Yes, the interconnects are shared between, and they're both going to be, these are going to be on both routers, but that's okay. So how do we verify it? We can do it one of two ways. Show IP protocols, and it's going to tell you again a routing protocol and the process ID that they're using. Or if you're using multiple process IDs, also neighbors will show you who your neighbors are and what state they're in, addresses, interfaces, timers, and all of that good stuff. You can do a show IP OSPF, and again that's going to be more specific to the individual device. It's going to talk about area backbone, it's going to talk about bandwidth, it's going to talk about if there's flooding, process ID, OSPF and its process ID, the router ID, the number of LSAs down here. It's going to give you some details. Show IP OSPF interface. And again, it's going to give you the interface, but a little bit more focus on the OSPF area. Again, process ID, router ID, network type, the topology costs. We're going to be talking about flooding, the appropriate serial interfaces, and again, process ID, network types again. Show IP OSPF interface brief. We'll show you the process IDs. We'll show you the areas. We'll show you the addresses, the costs, and the state that they're in. Is it a designated router, a backup designated router? Are they in different process IDs, in different areas? So show IP OSPF interface brief is a good one because it gives you a nice condensed material all in one area. So that's basic overview for OSPF v2. Let's talk about v3. v3 is just a clever way of saying for IPv6. Pretty similar. We do the IPv, or we do router OSPF or router OSPF process ID, but here we're doing IPv6 in front of it. All we do for this statement is the router ID. Everything else is done in a single line underneath each interface. IPv6, OSPF, process ID, and the area that it's in. That's it. In Packet Tracer, you may have issues if you do int range. Like here, normally these are all the same OSPF ID and same areas, so you may want to shorten that up by doing interface range serial 000 through serial 001, IPv6 OSPF 10 area 0, but in reality, that won't work. Just Packet Tracer does not like interface ranging the IPv6 commands, so it just is. Again, spheres of control, this guy knows about these networks, this guy knows about this network, this guy knows about these three networks. So again, the different interface statements. Here we're not doing network statements, we're doing these commands based off of an interface, not a network. So verifying OSPF version 3, again very similar to OSPF version 2, except here we're adding the IPv6 command instead of just the IP command. Same thing here as well. Show IPv6 route OSPF. That will show you the IPv6 portions for OSPF. Show IPv6 OSPF interface brief. Again, the PIDs, the process IDs, the interface IDs, costs, the state, is it a designated router, backup designated router, so forth. Let's talk about OSPF network types. This is where it's getting a little bit more confusing. Normally all of this was a CCNP level technology, but we're doing it here instead. So this should be fun. So I want to make sure I can do this as easy as possible. So I'm going to talk about OSPF network types. Point to point. This is going to be the simplest. It's going to be one router to another, point to point. We have a broadcast, which is obviously it's a point to point but through a switch. It's not very scalable, though it's a much more efficient manner of connecting large numbers of devices. It's multi-access. We have a non-broadcast, which is going to be more like frame relay, which we're going to talk more about that in the last CCNA class. But this is where everything will be sent as 3 separate unicast addresses. So even though it is going to be the same packet, it may be sent 3 different times. That way each router gets a specific one. Non-broadcast multi-access. Very similar to a broadcast, but when the switch receives it, it will actually be used as a unicast. Point to multi-point. Again, this is at like a very non-broadcast, but again, it's going to be one packet to multiple. So point-to-point, two routers. Broadcast multi-access, that's going to be multiple routers interconnected over some type of Ethernet network. We have a non-broadcast multi-access, that's going to be multiple routers interconnected in a network that does not allow for broadcasts. That's going to be more like a cloud solution, frame relay, MPLS, things like that. We have a point-to-multi-point, that's multiple routers. Point-to-multi-point is a multiple router interconnected in a hub and spoke type topology, typically over a non-broadcast network. And then lastly, we have these virtual links, which is a special OSPF network used to interconnect distance OSPF areas through some type of backbone, normally through some type of service provider or provider's edge. So with that said, there are some challenges in these multi-access networks. Main challenge is there's actually two. The creation of multiple adjacencies and the extensive flooding of LSAs, link state advertisements. So if we have this network, we have a simple formula for calculating the number of required adjacencies. N times n minus 1 divided by 2. So we have 4 routers. 4 times 4 minus 1 is 3, so that's 12 divided by 2. We have 6 adjacencies. 1, 2, 3, 4, 5, 6. It's going to be multiple adjacencies, multiple pathways to different locations, and each of these are going to flood LSAs. So we have to have some way of controlling that. And how we do that is a designated router. This is the solution for managing those adjacencies and flooding issues on a multi-access network. We have a backup version of the designated router called a backup designated router. Designated router, backup designated router. These are elected. All other devices are a designated router other, or non-designated router, or non-designated backup router. Only typically do brothers form adjacencies, and they form them with the backup routers, or the designated backup router. Designated others only send their LSAs to, again, the designated router, the backup designated router. They do it via a multicast address. The DRs use a multicast address, that guy, to send it to all other routers. That way only the designated router will flood with LSA advertisements. So instead of having all the routers constantly send to everyone else, we send it to the designated router, and the designated router controls it to all the other routers. The designated router and backup designated router, only the elections only are necessary on a multi-access network. So if it's not a multi-access network, it's not going to do the DR BDR election. So, role of the designated router is to control the LSAs to all the other routers. So the designated router will send out all and any LSAs to everyone else. It controls the flow. We have a backup one, and we have a primary one. If this guy goes down, this becomes the primary, and it takes over sending the LSAs. So how do we verify these? We could do a show IP OSPF interface or interface brief, and it will do that here. What state we're in, the designated routers and backup designated routers, and the adjacencies. Verifying again the adjacencies, you can do a show IP OSPF neighbor. If it's going to be a full designated router other, designated router, backup designated router, or a two-way designated router other. The two-way is not so common, but these four are. Full designated. If it's a full designated router, it has full adjacencies with the indicated DR neighbors. If it's a full designated or backup designated router, again it has full adjacencies with all of its neighbors. If it is a full designated router other, again it's a full adjacent with all other routers. So the two-way designated router other, it's the non-designated router or the non-designated router backup router has a neighbor adjacency with another non-designated router or backup designated router. Because again, this guy is going to form adjacencies with non-DRs or the BDR. This is going to do it with not just the BDR, but also the non-designated router. The default DR/BDR election process, the router with the highest interface priority is elected the designated router. The router with the second highest is going to be the backup one. You can configure them between 0 and 255. The router cannot become the designated router if its priority is 0. So if you always want to verify that this router won't become the designated router, priority 0. It's done on an interface. So if an interface priorities are equal, then the router with the highest router ID is elected. Priority first, router ID second. Here we're shooting for the highest number. 3 ways to determine the router ID. You can manually configure it, which we've been doing. If not configured, the ID is determined by the highest loopback IP address. If no loopback is there, the ID is determined by the highest active IPv4 address. If we're talking IPv6, we have to manually set the ID. Next, once you're a designated router, you stay the designated router until you fail, until the OSPF process is cleared on the failed DR, or if there's a multi-access interface on the DR that fails or is shut down, then another election process will occur. So if the DR fails, the backup designated router becomes the DR, and then another election is held for the backup one. If you are a DR and you fail, and the backup becomes the DR, and for whatever the first DR comes back online, it doesn't go through the election process again. The backup designated router is still the designated router until another failure occurs. So a common question is, how do I set the OSPF priority? We do that by, on the interface, setting the appropriate priority by typing in IP OSPF priority and a number. If we're talking IPv6 version, it'll be IPv6 OSPF the priority and then the value. How do we reset or clear the process? We type clear IP OSPF process in the privilege exec mode, typically on all routers. That will force a re-election. How do we propagate a default route in OSPF? If we have a route that we want to propagate, we do a default information originate, and that will propagate our default route. Typically, that's going to be an IP route, any destination, any subnet, send to next hop. Doesn't have to be an IP address. It could just be a specific interface. How can we verify the propagation of the default route? Is go to a different device and do a show IP route. And you should be able to see the route that's being propagated. How do we propagate a default route using OSPF v3 for IPv6? Again, same thing, same command, it's just done under the IPv6 router OSPF process ID number. We can also manipulate the hello and dead timers, but again, the hello and dead timers have to be the same on both sides. So if you manipulate one side, you have to make sure to do the other side as well. So if we want to modify the V2 intervals, underneath the interface, you would do OSPF or IP OSPF hello interval, set the interval. If you want to set the dead timer, it'll be IP OSPF dead interval, set the timer. Same general concept with the version 3 or the IPv6 version. Just again, make sure that you're doing IPv6 OSPF hello interval or dead interval and setting the time. Again, both sides must be set up first. You can't just do one side and leave it alone. So now that we talked about hello timers and dead timers and OSPF v2 and v3, how do we secure this? I know before we talked about doing passive interfaces on the LAN, and that's a good way to secure it, and that's kind of it, but is there more? Yes, there is. You can do 3 types of authentication with OSPF. You can do no authentication, you can do a simple password authentication, or you can do an MD5 authentication. And sadly, in this example, MD5 is going to be our highest level of security. So let's go ahead and talk about our MD5 authentication. So we will actually have an OSPF update packet with a secret key, gets a signature, and essentially we're comparing the signatures. MD5 authentication is enabled globally for all interfaces. We do that by typing in IP OSPF message digest key, the key, MD5, and the password. The area ID, authentication, message digest is also one of the commands. So we're going to look at a few examples of these, so don't fret. So to enable MD5 authentication on a per interface basis, we would do IP OSPF message digest key. Again, the same thing, but at the interface command. So let's go ahead and let's look at this in context. So here we have, first of all, we're enabling authentication using message digest for area 0. So router OSPF, the process ID. Area 0 authentication will use MD. So that turns on authentication MD for area 0. Next, underneath each interface, we're going to do IP OSPF MD key, message digest key 1. We're using MD5, and we're setting the password. And we can follow that through, again, all the interfaces. We can do the OSPF authentication message digest per interface, doing it this way. So instead of having it done under the router OSPF process ID, we can do this underneath each interface, and that would also work. How to talk about verification? Again, show IP OSPF interface. The specific interface, or even an interface brief, will give you the appropriate messages if they are doing the message digest or not. Here we have, again, our verifying our routing table. So let's talk about troubleshooting. OSPF adjacencies. Again, that's how we do our forming of our adjacencies with our neighbors. For simplicity, the interfaces are not on the same network. That will cause the adjacency not to form. OSPF network types don't match. The hello or dead timers don't match. The interface or to the neighbor is incorrectly configured or is passive. There's a missing or incorrect network statement, or authentication is misconfigured. Those are the key areas that will prevent adjacencies from forming. So essentially, when we're doing our transitional states from OSPF to full, so for the beginning, you turn on the device, it goes through a down state, an initiate state, a two-way state, then an X state, then an exchange state, then a loading state, then a full state. Keep in mind, this is for establishing the adjacencies, this is for synchronizing the database. What we want is a full state when possible. Troubleshooting commands are going to be the different show commands. Again, show IP protocols, show IP OSPF neighbor, show IP OSPF interface, show IP OSPF interface brief, gives you a little bit better, quick overview of everything, show IP OSPF. The nice thing here is these will kind of start sinking in when you start using them. There are so many show commands that not always remember what each of the show commands do. Time and practice. Components of troubleshooting OSPF. Is there connectivity issues? Yes or no? If yes, is the neighbor table correct? Is the routing table correct? Does traffic take the desired path? Is it functional? And again, the different show commands kind of help walk us through all of that. Troubleshooting neighbor issues could be just IP route, looking at, again, the different interfaces, the protocols. If the interface is accidentally a passive interface, if we're talking troubleshooting the routing table, looking at the show IP protocols, looking at the router function in the show run, looking at the show IP route to verify the routing table has the correct routes and that someone didn't fat finger them. When we talk about OSPv3, same thing, except when we're looking at our command, it's not show IP protocols, it's show IPv6 protocols. So do keep that in mind. And that is Chapter 5 in a nutshell. The big things here is, again, understanding designated route and backup designated routes, how to propagate default information or default routing information, how to set up message authentication, how to set OSPF authentication using the MD5 hash, manipulating the hash values, and basic troubleshooting. That's Chapter 5 in a nutshell. Thank you.